Okay, hello everyone. Welcome to this Global Vortex School webinar that we are having today on the topic of Vortex Layer Devices and how to use them for water purification and decontamination. This is the first webinar in our program for this specific topic. We usually do webinars on transformer oil, but the Vortex Layer Devices are also part of our product line. And so we've expanded our program to just give you may call it an orientation webinar to give you an idea what this is. In the text chat, somebody from the company will send you a guide detailing more applications for this device. So this is basically some of, you can call it a bonus for participation, I guess, this guide. And in case any of you has any questions during the webinar, you can send those questions into the chat. My colleagues are there to help you out, and I answer those questions. If we don't have enough time to answer your questions within the time frame of the webinar, someone will get back to you, and we'll answer your questions later after the webinar, because we'd rather not interrupt the webinar for questions. All right, so with this out of the way, I guess we can begin. So the problem of potable water, drinking water, is a big thing right now, and I'm sure you know that it has long been a problem for humanity, but now it's intensifying. So it's not solved yet. There is no indication that it's possible to supply enough water for everyone to drink with using just the traditional technologies of wastewater processing. Next slide, please. Okay, here we can see the traditional wastewater treatment facilities that use sludge fields and reservoirs that occupy very large areas. In this figure, you can see a traditional facility for preparation of potable water on a larger scale. The filtration system alone has a capacity of about 4 million cubic meters. It occupies about 20,000 square meters, and the volume of the settling tanks in this arrangement is about 500,000 of cubic meters. So this system can only remove solid impurities, particulates, and to disinfect the water. And this means that if the source water contains any soluble salts, for example, salts of heavy metals or phosphorus or arsenic or what have you, it's the size and cost of a facility to process such water can double or even triple. And at the same time, even if we increase the size of the facility, we don't necessarily have the ability to improve the degree of water purification. Go next slide, please. This here is a typical drinking water standard. Those change from country to country and from location to location, but this is a good starting point. And this table lists some of the requirements for the drinking potable water. And as you can see, those are quite strict. Unfortunately, it's safe to say that not everywhere in the world these standards are followed, especially if we're talking about some remote areas and settlements. In such cases, water is often taken from rivers or lakes like 100 or 200 years ago, and such water is consumed without much purification or anything. So these days, this is certainly not a good option. It's not healthy. For example, if there is even consider if there is a skinning plant nearby, that can discharge wastewater into that river, and you can have chromium poisoning, a possibility for the people that consume that water. Let's go next slide, please. Yeah, this is basically the continuation of the table. You can look at the requirements for the water. Okay, next slide now. Okay, good news. We think we have a bit of a solution to this problem. So there is a new method of treating wastewater using a new device that we call AVS. It's a Vortex Layer Device, and in a few minutes I will explain to you what that means. So let's consider this new method of treating water. There have been many technologies so far for purification of drinking water. We will not focus on those today. To a certain extent, they all do their job, albeit not quite with the results that we need. They all have a common drawback. The physical and chemical processes rely on diffusion methods, so something like reverse osmosis. And this is why attempts of reaching the same objectives by enlarging the treatment facilities are not particularly successful because the colossal capital costs involved, and those costs can make such extensive development unaffordable for many facilities or locations. Next slide, please. In this simple diagram here, you can see a process facility that has the capacity of purifying 200 to 500 cubic meters per day, so 200 to 500 tons of water per day. If necessary, the output of purified water can be increased if we use a Vortex Layer device of a larger capacity, or if we install several of them to work in parallel. This will just require us to install bigger settling tanks, which is a lot less expensive than other solutions. And after processing in this little facility, pipelines will take purified water to heating systems, for instance, to use in boilers and in central heating. Additionally, depending on the quality of the source water and the requirements for purity of the water and the standards, we can use either hydrocyclones or floating loading filters or sedimentation tanks to further improve the water. Such a facility does not require strong foundations or big industrial buildings to be installed. You can see in the diagram here in this plan, the footprint of the facility is just 122 square meters. And at the same time, again, it's designed to treat anywhere 200 to 500 metric tons of purified water per day, which is quite a bit. Next slide, please. So we have a different way of doing, a suggestion, I guess, of doing things. Let's take a closer look at our treatment process using the Vortex Layer device and talk about how effective they are. So the Vortex Layer device basically has a process chamber inside. It's that tube in the center of the device. This tube is located inside a magnetic inductor, and this inductor creates a rotating electromagnetic field. So it's much like an electric motor, but without the rotor. The tube, the process chamber, contains metallic ferromagnetic particles. And so when we power up the inductor, this rotating electromagnetic field in the chamber acts on these ferromagnetic particles, and they begin moving along very complex and chaotic trajectories. They collide with each other and go every which way. They collide with the walls of the chamber. So if water passes through this area, through this environment, along with impurities, then we have the combined effect of high power shock waves. Cavitation is a discharge of energy in water, and with the resulting ultrasonic waves that all have a combined synergetic effect on the water and help promote the physical and chemical processes that allow us to remove the impurities from the water. Let's go to the next slide, please. So this is what you can expect the AVS, as we call it, the Vortex Layer device, to look. This shape on the right, this is where the inductor is, basically. So we use additives in the process, chemicals, such as lime or iron sulfides and some others. In this process, all of it decomposes very quickly into ions, dissociates, and these chemicals react with impurities, forming insoluble substances and compounds in the form of metal hydroxides. In addition, water under the influence of all these factors breaks down into the H plus and OH minus ions, which in turn react with things, forming hydroxides and other things. And the presence of a high concentration of negative ions in the water just outright kills microflora or helminths or any parasites and anything. So we don't need as much chlorine to decontaminate the water, maybe not at all, or at least reduced by a factor of several times. The reduction of carbonate and non-carbonate hardness can also be achieved if we add lime or if we add flue gas, or rather not the flue gas, but what's important is its component, the CO. So when water contains fat or oil products, what we get in the end is insoluble calcium soap, and that can be quickly precipitated out of the water as well. Next slide, please. Okay, so to work out the purification technology, all wastewater streams are different pretty much. Every stream contains a certain concentration and percentage of things. So we need to work on the technology before we start a full-scale treatment. We need to know how much of what reagent we need to add into the process, how many ferromagnetic particles need to be added into the process chamber. So we use something what we call a laboratory process chamber. This is a small extractable, or rather maybe detachable process chamber that we put inside the AVS, and we put in the reagents, the wastewater, the metal particles, and then we stick it into the AVS 100 or 150 model into the devices, and we run the process and see the results, and adjust the process as necessary. And the AVS 100 and 150 model devices include those come equipped with these laboratory process chambers, so that the technology and the process can be fine-tuned. Next slide, please. Right, so the performance of the purification process largely depends on the rate of separation of the suspension into water and sludge. So the sediment, rather. The processing of the suspension in the process chamber of the AVS leads to an accelerated deposition of the solid phase, regardless of whether it was formed from a solution or if it was introduced externally from the outside. This phenomenon is due to the fact that solid particles in the process acquire the new properties. They lose their shroud, I guess, of the positive and negative charged ions held by the van der Waals forces. And so they descend through the liquid much faster. So in this case, Stokes' laws no longer apply to these particles. So if particles what it means is if particles fall and descend through a viscous fluid on their own weight, then the steady state velocity is achieved when this friction force, together with the Archimedes force, is exactly balanced by the force of gravity. In addition, the action of solidization is eliminated, and solidization is electromagnetic interaction between particles, ions, and molecules of a solute and a solvent. Solvation in aqueous solutions is called hydration, and we have a water here, so it's naturally hydration, right? So the molecular aggregates formed as a result of solvation are called solvates. In case of water, hydrates. So the high efficiency of water purification with the AVS technology makes yet another option viable. Most cities already have drinking water and wastewater treatment systems in place, I guess all cities, but they don't always operate at peak efficiency. Since the AVS doesn't take a lot of space, the footprint is quite small, as you can guess, and they don't require large industrial buildings. The units are practically mobile. You can put it on a cart if you needed to. So it's feasible to use them in the finishing stage of the process, in the end of the treatment process. So to bring the water composition to the maximum permissible concentrations of contaminants if necessary. And this could be especially important in the case of any epidemics or epizootics, so something like that. Next slide, please. It's quite expensive to build treatment facilities for water treatment using traditional technology for each individual small settlements, if we talk about remote places. But the use of the AVS devices removes and takes care of many difficulties because, for the reasons that I've already mentioned. This figure here shows a diagram of a process line that has a capacity to process about 50 cubic meters of water per day. And with a settling tank diameter of 2-3 meters, about 10 feet diameter, the area of the site will be just about 20 to 25 square meters. So there are two ways to arrange this. And the first option is shown here in the slide. There are the pumps 7 and 10, and the AVS are simultaneously turned on. Water is supplied from tank 1, the equalization tank, and additives are supplied from tanks 2 and 3. After treatment, such things as calcium, magnesium, magnesium hydroxide, chromium, zinc, copper, and what have you, as well as calcium salt precipitate. This suspension is fed by pump 7 into the hydrocyclone 8, in which most or the bulk of this solid phase is separated and enters the receiver 12 as sludge. So the water then sent to filter 9, where the final purification is performed. In this line, water can be passed simultaneously through 1 or 2 filters, depending on the actual volume of the water. And according to the information we received from our customers who already installed such process lines, if the velocity of the water stream is about 5 meters per hour, the continuous operation time of one filter is about 40 to 50 hours, after which the flow of water switched to the second pair of filters. Pump 10 does that, and the spent filter is washed with the water supplied by this pump for about 10 minutes. So we can always recover almost 100% of the filter's efficiency by just washing them with water. And given the high chemical resistance of polystyrene against the effects of any acids in the water, the lifetime of the filter spans like years. And the particles that we washed off in the form of sludge are then discharged into the sludge receiver, position 13, that is equipped with a replaceable container. And then purified water goes into the collection tank, and from there it's sent for biological revitalization or for further purification, maybe for use in heating systems. There's also the second option. We use lime milk or carbon dioxide as additives. And the main difference between this option is the replacement of expensive soda with flue gases. The gases are supplied to the process chamber by the fan 5 in position 5. In the AVS process chamber, carbon dioxide reacts with water, carbonate and non-carbonate components of the system, and transfers them partially into an insoluble state, thereby lowering the hardness of the water. Lime and aluminum additives perform the same function as in option 1. The difference is that when in contact with water, the water vapor contained in the flue gases also condenses, diluting the original water. It should be noted that the amount of water vapor in flue gases is very significant. So you can have about 9.5% of CO2 and about 18.9% of water. So it can be assumed that the condensation of water vapor in this arrangement will be almost complete. So for 1 cubic meter of this flue gas, the increase in water will be maybe 0.15 cubic meters of additional water. As a result, we discharge into the atmosphere practically pure nitrogen. This means that the process is very environmentally friendly, very small environmental footprint. However, an opposite process may be required. We may need to saturate the depleted water with calcium and magnesium. And in this case, the process line, we use a different process line. So the necessary ingredients are poured into containers 2 and 3, and then they're portioned into the stream of water entering the AVS. And this is followed by removing solid particles in hydrocyclones 8 and in filters 9. And if the water is free of such impurities, further treatment is really not required. Next slide, please. All right, and this table shows the results of operation of such a facility. The original water actually had a brown tint almost, and the analysis showed that the water contained up to 1.5% of iron and about the same amount of manganese, and it had humic acids in it as well. So sedimentation can be used instead of filtration to provide, say, a settlement with a population of maybe 1,000 people. Just 2 devices are sufficient, of which one is actually a spare. So if we calculate the necessary water consumption as 0.3 cubic meters per person, the process line worked like this. The actual consumption of water is measured, and then we determine the required process parameters. and lime milk, solutions of soda and iron sulfite. If we have any hexavalent chromium in the water, can be used as additives for further purification. Next slide, please. Right, so wastewater composition often varies widely. I've mentioned that already, with significant fluctuations in both the composition and the concentrations of pollutants. So let's consider the use of the AVS as chemical reactors in the reduction of hexavalent chromium and the precipitation of heavy metals in the form of hydroxides in the wastewater that is generated by electroplating or galvanic facilities. The AVS can be used as chemical reactors in the process of wastewater treatment to remove compounds of 6 and 3-valent chromium, nickel, iron, cadmium, and other heavy metals, and in some cases, in certain cases, cyanide compounds. AVS precipitates heavy metals in the form of hydroxide by neutralizing acid-base waters. The device reduces hexavalent chromium to trivalent chromium and simultaneously causes precipitation of heavy metals in the form of hydroxide. And the process also allows oxidation of cyanides to turn them into something rather harmless. This table here lists the characteristics of the composition and concentration of pollutants in wastewater coming from galvanic industry and from other industries where the AVS can be successfully used. The following requirements are imposed on wastewater being treated at treatment facilities using the AVS. So we need to have equalization of the composition and concentration of contaminants. The total content of pollutants, and that includes acid and alkali, should not exceed 10 grams per liter. No mechanical impurities should be present in the water. The water should not contain fluoride ions, oil products, any oils, or any other organic matter. The water should be separately supplied to treatment facilities and treatment of cyanide-containing and acid-alkaline fluids containing heavy metals. And when removing copper from wastewater, it's important that there is no bismuth or ammonia in that water because those lead to the formation of water-soluble copper compounds that are much more difficult to deal with. Next slide, please. Here you will see a visual representation of how we get rid of the cyanides after the AVS treatment. On the right here, you will see the precipitation process takes quite a bit shorter than what you have in the traditional method. And that sample is shown on the right. So on the left is a sample after AVS treatment, and on the right is a sample after a traditional agitator process. Okay, I guess we can go to the next slide if that video is over. Right. Here you can see how this works. Purification of chromium containing wastewater using calcium oxide reagent on the left, soda in the middle, and on the right, you can see the yellowish original sample before the purification was performed. As you can see in the slide, the retention time of the water in the AVS was about 3 seconds. And just after 20 minutes of settling in, you already have visible results. And after 24 hours of settling, you pretty much have clear water. Next slide, please. So on the reagents that we use in the AVS processes, the chemicals that we use depends on the type, nature, and volume, the amount of wastewater. It depends on the concentration of the pollutants and the treatment methods used. So in this case, to neutralize acids, alkali, and for precipitation of heavy metals in the form of hydroxides, we use lime milk, calcium oxide, soda ash, and other reagents, preferably lime milk, since it contributes to the formation of a well-settling, easily settling sediment. To reduce hexavalent chromium to trivalent, depending on the concentration, we use ferrous sulfite, bisulfite, or sodium sulfite as reducing agents. Then we use sodium hypochlorite or bleach maybe to oxidize cyanides and convert them into something harmless. So these reagents are used for wastewater treatment in the form of 5 to 10% solutions. Consumption of recommended reagents for wastewater treatment corresponds to the calculated stoichiometric amounts. Next slide, please. This here is you can see a schematic diagram of a wastewater treatment process using Vortex Layer Devices chemical reactor. So wastewater from an electroplating facility goes through a filter into an equalization tank. From there, it's pumped through a mesh filter to a Vortex Layer device. The content of pollutants in the water is continuously monitored at the outlet of the equalization tank by using things like pH meter sensors, chromium sensors, etc. And at the same time, the required amount of filtered chemicals, reagents, is supplied to the AVS device from reagent storage. The required flow rate of wastewater and reagents for each device is provided by portioning devices, and it's controlled by flow meters. And after treatment in a Vortex Layer device, the wastewater is checked for pH and for content of pollutants. Then it's fed to sedimentation tanks. The clarified water from those sedimentation tanks goes maybe to the sewage, or maybe it's reused in the production process with a proper additional treatment if that is necessary. And the precipitated sediment is periodically taken out of those tanks and removed. Right, so in the process of neutralization of wastewater and precipitation of heavy metals in the form of hydroxides, the pH value of neutralized water, which equals to or ranges between 7.5 to 9, can be considered a control parameter, which is the criterion for the completion of the process. And in the case of chromium-containing wastewater, with the concentration of hexavalent chromium of below 300 milligram per liter, the reduction of hexavalent chromium to trivalent with ferrous sulfide and precipitation of heavy metals in the form of hydroxide with alkali, for example, lime milk, is actually simultaneous. It happens at the same time. So when the concentration of hexavalent chromium in wastewater is above 300 milligram per liter, it's recommended to run the process in two stages. First, we reduce the chromium in an acidic medium at pH 2 or 3 with sodium bisulfate, and subsequent neutralization with alkali. In the cases listed above, reagents should be fed directly into the device, or maybe directly upstream from the Vortex Layer device, not in front of the pump. We do this to avoid overgrinding of the resulting solid hydroxides that we receive in the process. So when purifying wastewater from cyanide compounds, it's necessary to introduce an alkaline reagent solution to achieve a pH of maybe 10 or 11, and then an oxidizing agent solution, which could be sodium hypochlorite, to oxidize cyanides. After the AVS treatment, water goes to neutralization to achieve pH of 7.5 to 9, and precipitation of heavy metal ions in the form of hydroxides again. So the efficiency of the treatment facility's operation really depends on the choice of the process and method, on the selection and layout of the process equipment, the choice of the process modes, on control and regulation of the process parameters, and on the correct operation of the AVS units and the treatment facility design as a whole. So treatment facilities built in accordance with these requirements actually provide high quality wastewater treatment, and the content of pollutants in the resulting product water, I guess you could call it, does not exceed the MPC, or maximum permissible concentration standards. Right, so let's go to the next slide. Based on the experience of operating the AVS devices, the new methods and rational processes for puring wastewater to remove chromium ions and other heavy metals have been developed already, and this made it possible to significantly reduce the consumption of chemicals, something like a factor of 1.5 to 2 times, and to decrease the operating costs by the same amount, and to generally cut the costs of treatment facilities by, say, 20 to 25%. Treatment plans should include the following systems and components. We need filters for separating mechanical impurities larger than 1 millimeter from the wastewater of electroplating facilities before we feed them into equalization tanks. And we also need strainers, mesh filters after the equalization tanks. All right, so receiving tanks as well for equalization of wastewater, averaging out the concentrations of pollution, etc. We need pumps to supply wastewater and reagents, and the pumps should have the appropriate capacity. The hydraulic resistance created by the AVS device doesn't actually exceed some like 0.05 megapascal. So that's there for you. We need a system that regulates the supply of wastewater and reagents to each AVS device. Below the rated capacity of these devices, not exceeding that. We need flow meters for wastewater and reagents supplied to each of the AVS device. From experience, we know that induction flow meters work best for wastewater. We naturally need the AVS devices proper. We need devices for monitoring the composition of wastewater before and after treatment. That would include pH meters, chromium detectors, etc. We need sedimentation tanks to separate the solid hydroxide from the actual water when it is purified. And we need a reagent storage facility or unit that provides the supply of filtered and purified reagents that we can supply to the AVS through portioning devices that should also be installed. Next slide, please.
In our research and industrial use of the AVS devices in wastewater treatment processes for various industries have been developed and implemented. The process we present shows simultaneous treatment of chrome-containing and acidic or basic wastewater in alkaline environment. Both wastewater streams flow to equalizers, position 13, and are then processed by the AVS in position 16. At the same time, the 5 to 10% solution of lime milk and the reduction agent process solution are supplied to the AVS from vessels 3 and 9 respectively. The actual process occurs within fractions of a second. Next to the AVS devices are the mass exchange columns to improve the conditions of the simultaneous reduction of hexavalent chrome to trivalent chrome and formation of heavy metal hydroxides. After purification in the AVS, the wastewater with metal hydroxides flow to the settling tank 10 for clarification. To increase the rate of clarification and to reduce the size of the equipment, coagulant and flocculant are used. The ferrous and aluminous coagulant solutions are supplied to the settling tank from vessel 14, while the flocculant PAA solution is supplied from vessel 4. Lime is used as alkaline reagent. After the settling tank, the purified water goes to the clarified water collector 11 and can be either pumped for further purification to the sewer or back into the production process. The sediment from the settling tank goes into sediment collector 12, then dehydrated in vacuum filter 17, and is removed for disposal or recycling. Using this arrangement ensures purification quality exceeding that of the regulated maximum amounts, a reduction of reagent consumption by 1.5 to 2 times, a double reduction of power consumption, and 10 to 15% reduction of wastewater treatment equipment footprint.
All right, I hope you enjoyed this little video presentation of this AVS-based process. In this page here, you can see there an example results of using the AVS 100 apparatus for the wastewater treatment from an electroplating facility. The process that is basically described in this table of purification of chromium-containing wastewater was arranged as follows. Wastewater was in the amount of 10 to 15 cubic meters per hour with a certain concentration of hexavalent chromium. That water was pumped from the equalization tanks to the AVS. And at the same time, a calculated amount of approximately 30 to 60 grams per liter of iron sulfate solution was fed into this AVS device from the storage container by a portioning pump. In the AVS, the wastewater was treated with the iron sulfide solution, as a result of which hexavalent chromium was reduced to 3-valent chromium. The completeness of the chromium reduction was checked by express analysis using diphenyl carbazide and the colorimetric method. Disinfected or rather decontaminated effluents were then sent to neutralization and purification from 3-valent chromium already. So during the test, the consumption of iron sulfate was varied and changed between 80 and 100% of its stoichiometric consumption, and the pH of the medium was varied from 2 to 4, when the chromium 6 plus was reduced in an acidic medium, and then between 7.5 to 9.0 when it was reduced in an alkaline medium. A solution of lime milk was used to alkalinize the effluents. Ferromagnetic elements used were made of steel, and the total weight of the metal particles was about 200 to 300 grams. And the diameter of these ferromagnetic particles was 1.5 to 2 millimeters. And the processing time in the vortex layer was about half a second to 1.5 seconds. The initial concentrations of chromium 6 plus varied from 100 to 1,000 milligrams per liter. And the results of the testing of the AVS device in an actual industrial process are shown here in this table. All right, the neutralization of acid or base decontaminated chromium-containing water and the formation of metal hydroxides was tested in a similar installation using AVS with an inductor pore diameter of 100 millimeter and a 5 to 10% solution of lime milk as a chemical. The pH of the process varied in the range of 7.5 to 9, and the results of the test are also shown here in the table. So let's have a minute to look at the numbers here. All right, I guess we can go to the next slide. The regulation or adjustment of reagent supply can actually be automated depending on the composition of the wastewater supplied to the AVS. This can be monitored by the instruments and sensors installed before them. It's possible to correct the flow according to the readings of the sensors and adjust the process in real time, pretty much. This here on this slide, you can see the AVS-C complex. This, as you can see, this includes the AVS thing, the little donut-shaped thing in the center, I guess. On the left, you can see the control section, and with some settling tanks and filters on the right. Okay. Next slide, please. So this is what you saw in the previous slide, but it's a diagram now. So this is the AVS-K wastewater C a wastewater treatment plant, and C stands for containerized. So it basically means that the whole arrangement is built in a container. This is a small plant for removal of heavy metals based on Vortex Layer Devices. This arrangement includes the electromagnetic apparatus with ferromagnetic particles. This could be AVS 100 or an AVS 150. These two are different in terms of their capacities. By the way, we can go to the next slide right now. Thank you. Okay, these include in position 1, you have the AVS device, right? So the device itself consists of two sections. One is a control section, and the other is the process section. There are two containers with dosing pumps and agitators for supplying chemicals. Those are in position 6. There is the reaction tank in position 3, which is necessary to extend the reaction time of the treated wastewater with reaction. The supply pumps located in position 4. I believe these two pictures should be viewed together, but anyway. The tanks for mixing reagents are in position 5, and we use them before feeding into the process section that is in position 1. And the tank for sampling and capturing ferromagnetic particles in position 7. And the roof is equipped with 2 fans for cooling, that's position 8. There is a cabinet for installation of an air conditioning in position 9. And the cabinet for the placement of reagent is located in position 10. If we can go back to the previous slide, we can look at all of these things that were not on this slide. Let's go back one slide, please. All right. Never mind. Anyway, so this here is the AVS 150C. This is a mobile complex for wastewater purification from heavy metals, cyanides, arsenic, and even phenol. Wastewater treatment capacity here is 18 cubic meters per hour. And this would be a very good thing to install maybe in some more remote location, because it's easily transportable, it's easily installed, easily connected to utilities, and it's pretty easy to operate, really. So the dimensions of these of this container are really very comfortable. So length is about 4,800 millimeters, width is 2,100 millimeters, and the height is 2,500 millimeters. That's the whole container. As I've mentioned, the AVS is actually divided into two sections. You will see a bit more of that on the next slide. So the process section, the one that you can actually see through the doors of the container in the slide, it's about 1,000 millimeter long, just under 1,000 millimeter, like 900 millimeter wide, and 1,200 millimeter tall. And the control section is also very concise. It's about a meter in length, about 800 millimeters in width, and just under 2 meters in height. And the whole thing weighs approximately 4,000 kilograms, 4 metric tons or so. Next slide, please. So these are the AVS 100 and AVS 150 devices, and this is here you can see what I meant by talking about the process section, the control section. The process section is on the orange frame, and the control section that contains the controls and the coolant loops and everything that's in that cabinet right there. So these devices can be easily fit or retrofitted actually into the already existing water treatment facilities and lines. And what they do is they significantly increase the degree of purification, and we can actually easily achieve any maximum permissible concentration targets for this purification process. The capabilities of the AVS devices are not limited to wastewater purification. It's just something that works really well for the AVS, but there are also other, applications. The model range includes such things as the AVSP that is designed to make batches of emulsions or suspensions or uniform mixing of several different ingredients. We can regrind bulk products in suspensions to a particle size of less than 1 micron, so very fine grinding. You can imagine that when these magnetic particles or little metal pellets or cylinders spin around inside that process chamber, that creates conditions for very fine mixing or very fine, grinding. So there is a lot of applications of the AVS that can also be of interest industrially. But today we've concentrated on wastewater treatment. If this was something interesting, maybe we can, in one of our further webinars, we can return and talk more about this subject. And this pretty much concludes the material I wanted to present to you today. We've had quite a few questions in the text chat, and some of the questions are actually very good, and they do require a bit of consideration and talking with our chemists and engineers here. So we've taken your questions, and we will, whoever have not received an answer right now, we'll get back to you with your answers as soon as we have them. And with this, I would like to thank you all for attending and for listening to this information. And I hope to see you in our future webinars. Stay tuned and watch our website. We'll have more announcement of webinars on this and other topics as well later on. Again, thank you, and I hope to see you again. Bye.